Welcome to lecture number 20. This is I have written down some summary of what we did in the previous lecture. In this previous lecture, let's see what did we do. I had built a capacitor, parallel plate capacitor. I had shown in vacuum you would, if there were no dielectric material inside, then I had said that there will be if you apply a voltage V across this parallel plate capacitor, then you would get these black colored charges, and that will be sigma vacuum. And that will be sigma vacuum, which is sigma here stands for surface charge per unit area on the electrode plate. So that would be the charge you would generate, but if you put a dielectric material inside, then there will be some polarization. Consequence of that would be that additional charges, the red colored ones, would appear, and that would be sigma polarization, and in that case the total charge per unit area would have been written like this, and that had led to this kind of equation where we had related this sigma vacuum to epsilon naught E, and we had related this sigma polarization with P. Further, we had written that this polarization P is related to dielectric constant is proportional to electric field E, and through that we had defined a macroscopic dielectric constant K prime, or susceptibility psi is the same thing. P is proportional to E, and then in that proportionality either you define K prime or this susceptibility this electric permeability. So this susceptibility, not permeability, susceptibility. Permeability comes in magnetics. So this psi dielectric, the permeability, if it is a constant, then we said this will be a linear material, and we had assumed this to be proportional, and if you treat this as a constant. However, if this is P is not exactly proportional to E, though we are trying to make it proportional, in those cases it is traditional to make this quantity itself, though write it as if it is proportional, but make this quantity itself a function of the electric field. It's a function of electric field. So if this dielectric, dielectric susceptibility is function of electric field itself, then it's a non-linear dielectric. That's what we are going to do in this lecture. That's where we had left last time. However, before I start, I would like to do a little bit more on continuing from past itself. That is, before we discuss this non-linear dielectrics, let us one more time look at this polarization, this quantity polarization. It can also be defined as dipole moment, and this mu quantity which I had already defined last time, dipole moment per unit volume. Now, if I take this dipole, for example, if there is a dipole plus charges, minus charges, and this is written as Z, which is represents the valency, and Q is the fundamental charge of an electron, then the plus ZQ and minus ZQ are these two charges separated by a distance delta, then this dipole moment is defined as ZQ delta. By the way, this dipole moment is a vector quantity, it has a direction. It has a direction. I am just writing it as a scalar, but otherwise you could make this all these quantities, polarization and this electric field, all are really vector quantities. So if you write this dipole moment, and if there are n such dipoles per unit volume, because remember we are interested in polarization, which is per dipole moment per unit volume. So I am looking at if n this is dipole moment because of one dipole, and if there are n such dipoles per unit volume, and I am writing all of them are aligned. The reason I am writing all of them aligned are so that I can simply add them up vectorially also, since I am not putting a vector symbol here, and otherwise in principle you should do vectorial addition, but I am just trying to look at the scalar values, so I must make sure that they are all aligned so that it can be added in a scalar way. So if that is the case, then this polarization, by this definition that it is dipole moment per unit volume, then polarization would be equal to n times mu. Of course, again vector mu and vector p will be in same direction. So if that's the case, then given the value of mu, I can write this expression n times this ZQ delta, ZQ delta, and that's the polarization. And if this is the polarization, then remember we can write polarization as epsilon naught k minus 1, like this quantity here, which is what I have done. So this polarization I have written as epsilon naught k prime minus 1 times E electric field, which implies that dielectric constant minus 1, which is dielectric susceptibility, is equal to NZQ delta divided by epsilon naught E. Basically that is what this dielectric constant then would be defined as in terms of dipole moments. Continuing further, now what the part I wanted to also talk about today was, we looked at the bulk, that means a collection of dipoles, and that's how, so when we say dielectric properties, we are really talking of that of material, that means a collection of many dipoles. However, before we even whatever the value is in collection, as a collection of dipole, one must look at individual dipoles also, or we should look at individual at microscopic level also. So if you were to look, that's the part additional I wanted to add, if you wanted to examine dielectric behavior at microscopic level, where instead of applied fields, we work with local fields. Fields in a material, if you apply electric field, that's the applied field, but inside the material there will be a field which will be different from the electric field that one applies, and hence that field is being called the local field. So if you deal with the local fields, then we define this quantity polarizability as of an atom. That means we are now dealing with microscopic level, as this quantity alpha, which is same thing as which is written as mu divided by E, but this time electric field is local instead of electric field that is applied, which then I can write as P divided by n E local. Remember, n is, this is dipole moment per unit volume, and this is number of dipoles per unit volume, of course all aligned, and hence we are able to do this exercise in a scalar way. So it's the same expression we have written. And now if you look at the local field, what the local field is, if you were to take dilute gases, then this local field will be same thing as, you have a far apart, you have gases, we have gas atoms in a gas far apart because it is dilute, and hence overall you can treat it like a sort of vacuum in between, and therefore, well, saying that it's vacuum it will be inappropriate, but the point is that local field will be same as the applied field E. But that is not true in crystals. For example, if you were to take materials of cubic symmetry, if you took materials, crystalline materials which had cubic symmetry, in that case the local, if you had E as the applied field, then this E field will produce a polarization P such that the local field inside the material at a point would become equal to E plus P by 3 epsilon naught. This is relatively easy to prove, but I am not going to go through it in this class here. Often students do this in a physics class when they are first introduced to the effect of electric field on materials. In general, however, the way we will treat it is, since we don't necessarily going to be dealing with materials of cubic symmetry, we will say that in general the form of local field is something like E plus a factor beta, which is and P by epsilon naught. Basically I am drawing from the fact that for cubic symmetry this factor was, beta was 1 by 3, and in some other materials, in another symmetries, this could change to a more complex expression, but that some number which you are going to show up here, we can write that number as beta in general, in a general form. If that's the case, then we can write from here P as equal to alpha times n times E local, which is what I have done, P equal to n times alpha times E local, which now I am beginning to expand. P is equal to n alpha, and this E local we have written out here. So this is the E local we are going to use, this E local we are going to use and substitute in here E local, then you are going to get what you are going to get is, we are going to separate P and E. So we will take this on the left hand side. So I am going to write 1, which is for, because of this P 1 minus this n alpha beta epsilon naught, we are taking this on this side, is equal to n alpha E. And now again I can write, remember definition of susceptibility, dielectric susceptibility is or dielectric constant K prime minus 1 rather, is P divided by epsilon naught E, which is what this expression right here was, So we are going to use this expression and therefore write from here P divided by E, which I get from this equation, and I will write this as n alpha divided by this quantity in the bracket. I am going to write this as this quantity is E and epsilon naught is there, so I will get my susceptibility right here. So this is the expression I am going to use, and I have derived this before when I am doing this non-linear dielectrics. We are going to reuse this, and hence I have derived this part. Now with this I am going to start with today's lecture in earnest on non-linear dielectrics, and I will come back to this equation, I will point this out and we will use this in this context. So, let us get going on this non-linear dielectrics. Remember, one example yesterday we took was BaTiO3 barium titanate. We will use this as an example of a non-linear dielectric, and remember this I had shown this, the dielectric constant of this material as something like 3000, a very high dielectric constant material, and this is the material which is, and I said this is a non-linear dielectric. So today let us look at this particular material to explain what non-linear dielectrics are, and as we do, we are going to then generalize our ideas using this as a material, and mathematically we will connect this behavior of this material, dielectric behavior of this material, with this expression which we have derived right here. So I am going to connect back to this. So let us start with this. But even before we start talking about non-linear dielectrics, let me just give a quick rundown of certain facts which I am not going to prove, but they are just fact. Let us first start with what is a piezoelectric material. You may be wondering why I am talking about piezoelectric materials when I was talking about dielectric properties, but this will become apparent to you in a minute. What are piezoelectric materials? These are, if you apply stress, they produce polarization. And stress means mechanical stress. If you apply, they produce polarization. This is the, or charges, they produce charges. Or if you apply electric field, then they produce strain. Then you can also look at another kind of material, just one second, which is called pyroelectric material. In this case, if you apply a temperature gradient, if you change the temperature, in that case you get what is called as spontaneous polarization. What does that mean? As opposed to polarization. Here you had polarization, that means you apply stress, then you will have polarization. But if you do not apply, then there will be no polarization. Whereas in this pyroelectric material, if you apply temperature gradient, if you change temperature, then it will result in a spontaneous polarization. That means it is permanent in nature. Even when you remove delta T, some of it polarization may remain in the material. That means even when the temperature is taken back to its state, some polarization may remain. That means if you were to start with something, which is unpolarized, apply temperature, and polarization may increase, but and this will be spontaneous, so this will be sort of permanent in nature and will remain there. Third material which we look at is ferroelectric material, and this is what barium titanate is. And this is where I was taking you through, and all three of them are connected. The point I am going to make eventually is, if a material is a ferroelectric material, it has to be pyroelectric also, and if it is pyroelectric, it has to be piezoelectric, but not conversely. That is, if it is piezoelectric, that it need not be pyroelectric, and if it is pyroelectric, it need not be ferroelectric. But this way they would connect, and hence I am talking about all those three, though in principle I want to talk in this lecture, I mostly want to talk about this ferroelectricity, which is what relates to non-linear dielectric behavior. And this means, in this case, if you apply an electric field, then it produces a spontaneous polarization. That means a material initially may be in unpolarized state because of many different grains, but if you apply electric field, these dipole moments will align, and they are aligned to produce polarization. Of course, that happens in all materials. If you apply electric field, they produce polarization. But the point is, in this material, they will so polarize that once you remove the electric field, some polarization will remain, and that is what is meant by spontaneous polarization. So, these are the three types of materials. How are they connected? Let us look at this one time. Let us look at now, and take this what I am writing as a statement of fact, because it is not part of the course here. We have 32 point groups or crystal symmetries. Out of these, 11 are centrosymmetric. Of them are centrosymmetric. For example, a cubic crystal is centrosymmetric. There is a center about which there is a complete symmetry. 21 of course then are non-centrosymmetric. Out of these, at least 20 are at least 20 have one or more polar axes, and these materials are piezoelectrics. It is the non-centrosymmetricity, the point I am making is that it is the non-centrosymmetricity which gives rise to piezoelectricity, and this as an example I am going to show you in a minute. So, this gives to piezoelectric material. Now, if you look at this, and then out of these 20 there are 10 which are polar, and these are the ones we are interested in, and they can be spontaneously polarized. Spontaneously polarized. Spontaneously polarizable. They all are crystals possess permanent dipole moment, all are pyroelectric because they can be spontaneously polarized, hence they are all pyroelectric. Remember, you need spontaneous polarization for pyroelectric material, of course for ferroelectric also. Some of these are ferroelectric also. So, these ferroelectric are always pyroelectric, and all pyroelectric are piezoelectric because they belong to this 20 of the point groups which are non-centrosymmetric. Now, what do I mean? I will show you through a picture and then through a schematic, and that will illustrate the point a little bit better, and let us do that as follows. For example, let me show you something which is first let us start with centrosymmetric. Which means I am taking this as an example. Maybe I do it here itself. This example I will do right here. If you were to take a material which look like this, and in which I am going to make dipole, since structure is centrosymmetric, so dipoles existing in it would also be centrosymmetric, and hence I am going to make it something like this, let us say. what have I drawn? I am drawing as if these are the directions of the dipole moment, this direction down, this direction on right, this direction on the left. Similarly here for different locations. What will happen? In this case, all the dipole moments will cancel out. All the dipole moments, one on the top, one pointing this way will cancel out with one pointing out this way, one pointing out this way will cancel out one pointing out this way, and net polarization would be 0, because net dipole moment is 0. Net dipole moment is 0, so net polarization would be 0. If you were to, for example, apply stress on this material, a compressive stress, then let us say this material got compressed in this direction. So, because you applied compressive stress, mechanical stress, if you apply on this, what is going to happen in this case? In this case, I am going to show that this dipoles in this direction getting stretched because you applied stress. And this is, remember, this is only a schematic which is showing you direction of the dipoles, and the length of this is showing you the magnitude of the dipole, direction and the magnitude of the, here the magnitude was equal, it was being drawn in a symmetric way. Here in this case, this is long and this direction is shorter, because when you applied the stress, sort of d has shrunk, whereas it expanded in this direction, the d has expanded, the distance between the dipole, the positive and negative charge centers has increased. So if that is the case, then as you apply stress, this happens, but then again this dipole moment pointing this way will cancel the dipole moment pointing this way. Dipole moment pointing this way will cancel with the dipole moment cancelling with this way, though dipoles have changed, dipole moments have changed, but net dipole moment continues to remain 0 and P is equal to 0. This is the nature of the centrosymmetric structures, that if you apply electric field, if you apply stress, there is no change in polarization, whereas in piezoelectric material we expected that when you apply stress, then some polarization must be generated, and that we will see will come because of non-centrosymmetry, and that's what. But if it is centrosymmetric like these 11 point groups, in that case, like for example cubic material, in such cases even if you apply stress, polarization will be 0. Of course it can still be linear dielectric, that means if you apply electric field to this material, these dipoles will change, dipole moment will change, and there may be a net dipole moment, there will be some net dipole moment as a consequence. So that would still happen, this will have some dielectric constant which will be a low dielectric constant, but we will see what happens if this was non-centrosymmetric and what happens as a consequence of non-centrosymmetry when spontaneous polarization becomes possible. These are the two aspects we need to look at as heading towards barium titanate. So now, so this is a centrosymmetric. Now let us look at a non-centrosymmetric, now let us look at non-centrosymmetric crystal. In fact, let us add the word non here therefore. Now let us look at one of the non-centrosymmetric. Let us take an example like this now. What if these dipoles were pointing like this? And it was nicely symmetric, but now in this form. Now notice this is not centrosymmetric. The inversion symmetry is not there, therefore it is not a centrosymmetric structure. But in this case polarization still 0, polarization is still 0 because these three vectors, dipole vectors, when added vectorially would produce P equal to 0. The length of these each dipole I am showing extent, that means it shows you the magnitude of dipole, direction and the length shows you the magnitude of the dipole, they still are equal, and hence what will happen is net polarization would be 0. Now in this case let us apply stress to the crystal, and what happens? When you apply stress, let us say again compressive stress, something like this, you applied a compressive stress on this material, but now something will happen. As a consequence of this compressive stress, let us say now this has become like this. these two have gotten elongated, these two have gotten elongated, this has shortened in comparison to here because of the stress which is applied. Now what do we think? Now if this happens, you are going to get a value of P. Polarization is not 0. Remember, these three vectors when added would not result in 0 now. There will be net dipole moment in this direction. There will be a net dipole moment which you are going to see as a consequence in this direction. You are going to see a net dipole moment because of you have applied a stress, and these materials are piezoelectric. This is an example of piezoelectric material. Let us go back. If you remove the stress, it can go back to the state, and hence this is not spontaneous. This polarization which we get is not spontaneous, it is not permanent. It is not permanent in nature. It can go away. Such are piezoelectric materials which I had pointed out. Non-centrosymmetry leads to one or more polar axes, and you have now seen the polar axis. In one direction, which is this direction, polarization can result if you apply a stress in this particular schematic. So what you get is a piezoelectric material, and this piezoelectric material was defined as if you apply stress, it produces polarization. It does not say spontaneous, however. Now, so if you further move forward and take another example where you will see that we could also have spontaneous polarization. What do I mean by that? That means even when you have not applied, and if you have not applied any stress, still but this is not, so this is not ferroelectric, I should write, that is all I should do, because it is not spontaneous. Now I am going to give you an example of ferroelectric material. Let us say we go to third case, which is, let us say, ferroelectric. Of course in this case also it will be piezoelectric. Ferroelectric materials are always piezoelectric or pyroelectric for that matter. But now in this case what I am going to do is, let us take a structure which is like this. Let us say we consider ions. Here is negative ions. Let us say these are negative ions which I am drawing. These are negative ions, and here is positive ion. Let us say these are the positive ions. Sorry. So these are the positive ions. What do you see? You see the center of charge of positive charge, center of positive charge and center of negative charge are not identical. So there is some distance between, there is some separation between center of positive charge and negative charge. If such a situation arises, this material will have some polarization which is not equal to 0. That means even in its native state it has a polarization. Such materials are ferroelectric. And if you apply since it is ferroelectric material, it can also demonstrate piezoelectricity, and this you can see as follows, that if you were to apply stress in this material, the fact there is a spontaneous polarization, even when you have not done anything, P is not equal to 0, implies that it is a ferroelectric material. Since ferroelectric material is also a piezoelectric material, therefore let us look how that piezoelectricity plays out in a ferroelectric material. So you apply this stress, and what happens as a consequence is that you have these centers of negative charges and these ion positions further change, as opposed to here they have slightly moved up further with respect to these centers of negative charges, and in this case you have P plus some delta P, some additional polarization. This is showing you a behavior which shows piezoelectricity. Of course, if you take away the stress, it will come back to the state where there will be again some net polarization, but of lower value, which is P, of the lower value which is P. So that polarization will continue to be there. So this is the nature of ferroelectric material, which is where we are heading. That the point you need to remember is that the non-linear dielectrics which we are about to deal with, I am going to talk about more about ferroelectric materials. These are the non-linear dielectrics. They must have they must be non-centrosymmetric. They must be non-centrosymmetric and must have a must be polar materials. These must be polar materials, so that there is a spontaneous polarization. There is a spontaneous polarization is there, and as a consequence of which ferroelectricity will arise. So let's, in order to look at this material, let us look at okay. So now let's start with barium titanate as an example of this ferroelectric non-linear dielectric, non-linear dielectric, ferroelectric. I am using it interchangeably. Let's use barium titanate as an example of this and see first physically. Let us see how this situation, which I have shown you as schematic, how that is realized in actual crystal. Once we have seen physically as to what happens, then we will go through the mathematics of it and finish off this lecture. To understand ferroelectricity in barium titanate, let us see it through this slide, these pictures I have put here, and in order to understand ferroelectricity, let us start with a structure in barium titanate which is not ferroelectric. So what we do is, we start with a temperature which is greater than 120 degrees centigrade. In this case, the structure is cubic, and since structure is cubic, as you know, cubic is a centrosymmetric structure, so it is not possible for this material to be ferroelectric, because cubic centrosymmetric and you require non-centrosymmetricity for any ferroelectricity. So now, since this is not ferroelectric, we are calling it paraelectric, and we are borrowing this name in much the same way as you have ferromagnetism and paramagnetism. A ferromagnetic material above some temperature called Curie temperature turns into a paramagnetic material when it loses its magnetism. So similarly, since this material at some is going to be ferroelectric, but at T greater than 120 degrees centigrade it loses its ferroelectricity, hence we are calling it paraelectric in the same analogy, and it has lost its ferroelectricity because it is cubic All right. So let us try to understand this cubic structure first, and then we try to go on to ferroelectric phase. So what do we have? This particular material is simple cubic, and basis set of atoms is, it is a 5 atom basis, that is 1 barium atom, 1 titanium atom and 3 oxygen atoms. And at what location? Barium is at 0 0 0. That means if I draw a cube like this here, this cube drawn here, then at the corners we have what are 0 0 0 positions. So if you wish, what we can do is we can put a coordinate axis something like this. This is x, this is y, and this is z. So we can put a coordinate axis something like this, and what that means is that barium is at 0 0 position, then it is at this position. Let us say this is x axis, this is y axis, and this is z axis. So this is 0 0 position, and if you displace then by lattice parameters, which is a in this case, then so if you go from here to here, you get equivalent atom, that is also 0 0 0 position therefore, or you move by lattice position, lattice distance a, then again it is 0 0 0. So these corners are 0 0 0 positions. 1 barium atom these are, so blue ones are 1 equivalent to corner of cube means 1 barium atom. In the center at half right here, half we have a titanium atom, and on the FCC like positions, that means on, let us say half 0. So if this is x, this is y, and this is z, then in that case half 0 is move half in this direction and half in this direction. So this is half 0. So this is half 0 oxygen atom, and equivalent, if you move by lattice parameter you get an equivalent atom. So therefore this is also equivalent half 0 atom. Similarly you got half, if you look at half 0 half, I should erase this. So if you look at this half 0 half, so I move half and then and half this way, 0 half is right here, and z you move half. So you get this particular oxygen atom, and this is an equivalent oxygen atom. Every time you move by lattice parameter, you only get a equivalent atom. And similarly the 0 half, that means 0 half and half, 0 half and half. So, you get this at particular atom 0, half, half is this particular atom, and this is equivalent atom, and this particular atom is on this face right here, this face, and this particular oxygen equivalent oxygen atom is on this particular face of the cube. So, this is a simple cubic structure. It is centrosymmetric, and therefore, as a consequence, you see where is the center of positive charge. You see these are barium atoms. Its center of positive charge is right in the center, and titanium, of course, is right here at the same place at half, half, half. So, center of all the positive charges is at half, half, half. Similarly, if you consider this octahedron made by this oxygen atoms, center of that is also at half, half, half. So, center of negative charges due to oxygen is also at half, 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 and therefore, the center of positive charge and center of negative charge are coincident on them, on each other, and the consequence is, therefore, what we will have is total polarization as equal to 0, because there will be no net dipole moment in a unit cell, and therefore, polarization will be 0. Centrosymmetric structure leads to that. So, that is a simple cubic structure. So, now let us look at ferroelectricity. How does ferroelectricity comes? Now, suppose you start cooling it down to below 120 degrees centigrade. So, if you go down to at temperatures less than 120 degrees centigrade, then what happens? And in fact, from 120 centigrade, I should write maybe from something from temperatures anywhere from room temperature to onwards to 120 degrees centigrade. In fact, from temperatures even less than room temperatures to 120 degrees centigrade, the barium titanate goes into a tetragonal phase. So, barium titanate goes into a tetragonal phase. So, phase transformation happens at 120 degrees centigrade as you cool it down. Cool this down from temperatures greater than 120 degrees centigrade, and then as you cool down to less than 120 degrees centigrade, at 120 degrees centigrade, this particular material changes its phase and it becomes tetragonal. So, this particular tetragonal phase is ferroelectric, and how does this ferroelectricity arise is what I want to show you. So, how does this happen? So, let us look at this. So, what is happening is, go back here to this particular diagram of simple cubic. Now, imagine what you are doing is that you are pulling this axis up, you are elongating this axis a little bit and maybe squeezing this little bit. So, what you have in a tetragonal one is that this particular dimension is 0.403 nanometers, whereas these two A and B axes are equal and they are 0.398 nanometers. Now, this tetragon I have formed by placing the barium atoms. So, these barium atoms again we are calling at 0, 0, 0. So, this is the 0, 0, 0, 8 barium atoms which form the cage, tetragonal cage. Now, we are going to place all other atoms with respect to this particular cage. So, if you look at so now what I am doing is that in order to explain to you what has happened, that imagine for this cage, this blue line, particular blue line going through is the center line, is the center line of this cage. What is this diagram? This diagram I am showing this particular face. This particular face is being shown on this diagram. In other words, I am showing you 1, 0, 0 projection of barium. I am showing you a 1, 0, 0 projection of this particular barium titanate tetragonal structure. So, okay. So, if that is the case, so if what I am doing is I am making a center line and I am drawing a blue center line. Now, think like this, that this whole look at the simple cubic, there was a this is the octahedron formed by oxygen atoms here, by these six oxygen atoms had formed an octahedron. Now, imagine this octahedron slightly shifts down. This octahedron has slightly shifted down with respect to the central line. So, what I am showing you here is, now in this case, this is gone here. So, now what I am showing you here is that with respect to this blue line in the center, this particular oxygen atoms have moved slightly down. What am I showing you? That this is the oxygen atoms, these 4 oxygen atoms. So, if I take 100 position, then this particular atom is shown right here, this particular atom is shown right here, and these two will fall on top of each other, and that is the atom, oxygen atom here. And with respect to this blue line, which represented the center of the cage, this barium cage, then this oxygen octahedron has moved down a little bit by this 0. So, this distance is between blue line and the black line 0.006 nanometer, it has moved down. Okay. Not only that, something more has happened. In fact, this octahedron has distorted. These two oxygen atoms have not simply just displaced down, they have moved, they have been squeezed down, these two atoms have been squeezed further, and they have displaced by, with respect to this top line, they have not just moved 0.006, instead they moved 0.009. So, this octahedron has even, in fact, from the simple cubic, this octahedron has distorted also. So, these two things have happened. Now, if you look at the titanium atom, then this particular titanium atom with respect to this blue center line has slightly moved up. This is the distance, this is the arrow showing spacing between the blue line and the red line, and this titanium atom has slightly moved up by amount 0.006. So, that is what has happened in this barium titanate structure, and consequence of that now will be, now you can imagine, you can think like this, the center of these barium, center of positive charge due to these barium atoms will of course will be smack in the center where the blue line is, the center of all the positive charges due to barium, and titanium charge is positive charge due to titanium is where it is shown, right, that is where the titanium atom is. So, somewhere net positive charge will be above this blue line, whereas if you look at the oxygen, now oxygen cage right here, the net positive charge will be, negative charge would now be slightly below the blue line, and therefore, now the center of positive charge and centers of negative charge are not going to be coincident on top of each other. Consequence of that is that in this particular material, P will not be equal to 0. P will not be equal to 0, and that will there will be net polarization or net dipole moment in cell, and in material there can be therefore a net polarization, and such a material therefore we will say it. So, this particular material therefore acquires ferroelectricity. Ferroelectric. So, this becomes a ferroelectric material. The fact that it has a spontaneous dipole moment now that it has a spontaneous dipole, this material, in this structure, tetragonal structure, what I have described here, the fact that it has a net dipole moment, polarization, that means it is not 0. Therefore, this material can be ferroelectric. In fact, since there is a spontaneous polarization, therefore, for sure it is pyroelectric. It is pyroelectric, and as you know that some pyroelectric material can be ferroelectric. In this particular instance, this is also ferroelectric. All right, and all this has happened because the structure is not centrosymmetric. So, this is the point which needs to be understood. Why? Because the structure ferroelectricity in barium titanate arises. So, as a consequence, what happens? Before we go on to describe this particular material, let us one more time do the mathematics of it as to what happens then, what is going on in this material, and we will describe this by using the same equation as here. Remember, I had shown you that dielectric susceptibility is given by this quantity. Now imagine what happened. In fact, I want to speak about one more thing in terms of why this structure has happened like this. I want to connect to something I had discussed earlier also. You will recall, you go back a lecture and you will recall I had drawn a curve something like this. I was talking in terms of, I was talking about dipolar mechanism for in context of dielectric constants. I was saying, I was talking about dipolar mechanism, and I had plotted energy versus position, and I had position for, and in this I had shown a plot which was something like this. And I was saying there could be two equivalent positions, these two positions, and atoms could hop, ions could hop from one to another position, and from this position, there are two positions in energy are equivalent positions, so they are equally probable. That is what we were talking about. Now, let us connect this idea back with this ferroelectric, back with this ferroelectric idea right here in this structure. And what does it mean? What is this hopping involved? I was talking about in dipolar mechanism, there is hopping involved, and what is that about? Now, we will connect that and understand its dielectric property. So, now I will come back again to the simple cubic structure, which was symmetric, nice symmetric structure. Let us see how we are going to get this tetragonal structure. What we will do is, let us do this. Take these 4 oxygen atoms, in order to make tetragon, start squeezing these 4 atoms slightly inside. while extending these two oxygen atoms, pull them up, pull this up and pull this atom down. Imagine stretch these two particular atoms stretch farther apart, and as consequence these two 4 oxygen atoms, pull them closer. If you do that, what is going to happen? You see, the titanium is nicely sitting in the center. If you want to squeeze these oxygen atoms in, then the only way out is that this titanium atom should pop out of the pocket. Either it can go up or it can go down. So now this is what you can see here, that as you convert it to a tetragonal structure, in this structure that I have shown, that what I am showing you is, this is what has happened is, this titanium atom decided to pop slightly out of plane of these 4 oxygen atoms, and it went up a little bit, and this whole cage which I am showing you here, this cage formed by oxygen atoms, has moved down a little. So titanium moved up a little bit, and oxygen atoms, cage of oxygen atom moved down a little bit, and this all happened because you squeezed these 4 atoms in, ions in and these 2 ions farther apart, pulled them apart, and that led to a tetragonal structure. So this is what has happened, and hence this kind of structure formed. But notice that instead of titanium popping up, it was equally possible that this titanium would have popped down. It could have popped down also, and in which case this oxygen cell could have moved slightly up. Those will be equivalent structure. The one I have shown you is, in this case titanium has popped up and oxygen moved down, but you can easily imagine this cage moving up and this titanium moving down. So these are 2 equivalent positions, and now refer back to these 2 equivalent positions. So these are the 2 equivalent positions for titanium ion. Now you can see, so this is, now if you apply electric field, if you apply electric field in particular direction, then one of these can become more favorable, one of these can become favorable, and that nature of electric field will decide therefore whether titanium would pop up or titanium will pop down, depending on which of these 2 positions becomes more favorable. And it is this mechanism which then leads to dielectric constants, or the high dielectric constants in barium titanate. With this connection, let us move on. Now if you look at the mathematics of this, then again go back to this structure which I was talking about. That dielectric constant or dielectric constant K prime connected to susceptibility is given by n alpha epsilon naught 1 minus n alpha beta epsilon naught, and remember this alpha is the quantity which is called polarizability. Now suppose you are at high temperature greater than 120 degrees centigrade, and at that high temperature what is going to happen? You are going to have dipole moments, but the kT temperature will try to randomize these direction of these dipole moments, and as a result, so if I have a dipole pointing this way, some dipole pointing this way, some dipole pointing this way, some dipole pointing this way, in all different directions, because of this barium titanate crystals, I have this way, I apply electric field, which will then, all these dipoles will, whatever the polarization which has been created because of electric field, sorry, so cubic, we are talking about cubic barium titanate at temperatures greater than 120 degrees centigrade, there is no permanent dipole moment. When I apply electric fields, direct dipole moments are created, and these dipole moments are pointing in random directions, any direction they are pointing out, and this kT energy is trying to randomize them. Now what happens when you cool down? As you begin to cool down, the effect of kT, that means effect of temperature trying to randomize the polarization direction, will become lower and lower, and hence your dipole moment is, net dipole moment is going to increase in the direction of electric field that you are applying, because polarization dipole moments will like to follow electric field. It is only the kT energy which is trying to disturb them from out of their position. So as you cool down, your polarizability is going to increase. This polarizability is going to increase, and high temperature this term may be very small. In fact, let me write this expression one more time. So the expression I had written is that dielectric is equal to K prime minus 1 equal to n alpha epsilon naught 1 minus n alpha beta by epsilon naught, and high T, high temperature, n alpha beta epsilon naught is small, because very high temperature this alpha is small, temperatures are trying to temperature is trying to randomize all the dipoles, and this quantity is small, you can neglect it in comparison to 1 and you will get some small dielectric susceptibility value. But as you lower the temperature, and I am saying start from T much greater than 120 degrees centigrade, and we are heading towards 120 degrees centigrade. So, as you lower the temperature towards 120 degrees centigrade, what happens? Your alpha is going to increase and this term is going to increase. This is going to increase. So, n alpha beta by epsilon naught is going to increase. What happens when n alpha beta epsilon naught approaches 1? That is an interesting question, because you can see as it approaches 1, this term, this quantity is going to blow up. Dielectric constant will blow up, it will start going towards infinity. You can see this because this will become divided by 0 and this number will blow up, and dielectric constant of material cannot be, it is a polarization, it is a dipole moments per unit volume. The dipoles cannot go to head towards infinity. So, something is wrong, this cannot happen, physically not feasible. So, something must give. In fact, that implies will tend towards, go towards infinity. That cannot happen. Something must give, and what happens is phase transformation. And this is because of this reason, at a temperature of 120 degrees centigrade, when this value is tending towards 1, and crystal would fly apart if nothing happened, and since crystal does exist, so what has happened is it requires a phase transformation and you get what is called as tetragonal phase. Tetragonal phase, which I have shown of barium titanate. So, that is what you start getting a barium titanate tetragonal phase is what you get. Now, if we postulate that this polarizability which we are talking about is proportional to some constant divided by T. Remember, I said as temperature decreases, polarizability increases. So, if you postulate that it is inversely proportional to power 1 of T, then in that case we can write dielectric susceptibility as, or dielectric constant as C prime by T divided by epsilon naught. Remember, what I am doing is I am substituting in here for n alpha. I am substituting into this expression, I am substituting value of n alpha is what I am substituting in here. So, if I do that, this is epsilon naught minus C prime beta by T, which I am going to write as C prime by epsilon naught divided by T minus some C prime beta by epsilon naught. And if we define C prime beta by epsilon naught as some temperature Tc and C prime by epsilon naught as another constant by, let us say, give it a name C, then in that case I will write dielectric susceptibility as, or dielectric constant as, equal to some C divided by T minus Tc, which is well known Curie-West law. So, that is a well known Curie-West law, and what is it? And if I therefore now what I can do is I can plot susceptibility versus temperature versus susceptibility, and in that case for temperatures, 1 by susceptibility is what I want to plot. Remember what happens, let us say this is Tc, so this is Tc, remember this is going to go something like this. As we lower the temperature, susceptibility increases, and therefore 1 by susceptibility decreases, and what happens at this point, a phase transformation occurs and a phase transformation occurs, and otherwise this would have gone down, this would have continued to go down towards a value of 0, because, and that means susceptibility would have gone to infinity, something like this, and because of phase transformation we get a behavior which is something like this. It starts increasing again according to this expression, and this is what is called as Curie temperature. In finality, in another 5 minutes, let me try to now show you the behavior of this particular barium titanate material. That if you look at ferroelectric materials, they will show you much the same way as ferromagnetic materials. They will show you what is ferroelectricity then. What is ferroelectricity? What it means is that if you have such a material, then it would show a behavior which is something like this. A hysteresis between polarization and electric field. So, if you apply electric field, it produces polarization. Remember, you apply magnetic field, it produces magnetization and in a ferromagnetic material, and this is a very similar thing, and that is why the name ferroelectricity has been given here, because it is a curve between P and E. There is a hysteresis. As you apply a field, electric field, you get what is called saturation polarization. This is the saturation polarization in this material, because this titanium atom, remember, has popped out in one direction, there is a and then popped out, and you get some polarization, very large polarization, and when you remove this electric field, you get some remnant polarization. This is the remnant polarization, and if you want to remove this remnant polarization, you have to apply a coercive field EC, and this story repeats if you go in other direction. So that means if you apply a field and you can reverse the direction of polarization and remove electric field, there still is some minus PR or plus PR, which is this polarization which is still available in this material, and hence this is a good memory material. You can use electric field to apply, you can apply electric field and create polarization, remove electric field, and the state remains. If you apply electric field up to here, for example, you can, and then remove the electric field, you will have this PR electric field, call it bit 1, and if you want to create bit 0, then what you have to do is apply electric field up to this extent right here, and then remove that electric field, you would have written minus PR, let us call that 0, and hence you can write 1 or 0 on it, and this could be a good memory material. But this is the behavior of this material, and these are ferroelectric material, very important class of materials in engineering. Thank you.